This presentation covers work, energy, and power and their relationship between each other. The product of the force applied to an object over a distance in which the object travels is a result of the force. Force and distance have to be parallel to each other, so work is force times distance, or the distance the object is moved. We measure work in joules. Here's an example of work. So a student lifts a 50-pound ball 4 feet in 5 seconds. We want to know how many joules of work did this student use. The first thing to do to figure out how many joules of work the student completed is to convert the units from English standard units to SI units. To do that, I know that 1 pound is 4.45 newtons and 1 foot is 0.305 meters. Here's a nice little formula to do it for that. So it's easier to know that a 50-pound ball times 4.45 newtons gives me about 223 newtons. 4 feet times 0.305 meters gives me about 1.22 meters. I solve for work. I plug in my force, which is 223 newtons, my distance of 1.22 meters, and I get that the student did about 271 joules worth of work. Energy is the ability to do work. Light, heat, mechanical, chemical, and electrical forms of energy can be used to exert a force over any distance. Roller coaster is an example of a mechanical type of energy. NASA solar sail takes light and transmits it into movable energy, and then fuel cells allow us to do very similar things as the solar sail. Potential energy is energy that it's stored. Quite often you usually look at this as gravitational energy. Dams are a really good way to show the amount of potential energy there is. Fossil fuels, another way to show potential energy. Batteries, yet another way to show potential energy. Kinetic energy is most often thought of as energy in motion. Kinetic means to move. So kinetic energy, think of it as anything that moves, whether it's small or large. Energy transformation from chemical to kinetic. We eat, we move. Radiant, light, to chemical. I take light, and in the case of this picture of the nice young woman you see standing there, she can take the plant, which is pulling and making energy from light, and turning it into chemicals that are in the water there. We can take electricity and cook a turkey. It's another way to show energy transformation. Some renewable energy sources, biomass. Ethanol fuel is the one you hear the most. In this country, we typically use corn. Many other countries, they use sugar, as well as quite a few other different types. Corn syrup is another one that I've heard of quite often, that they turn into biodiesel or other biofuels. Hydropower, one that you fill up the dam and you just let it run through. As long as the water keeps running and the rivers keep flowing, it will continue to provide electricity. Geothermal, of course, we've talked about wind and we've talked about solar. Non-renewable energy sources, going to be almost any fossil fuel, not considered renewable, and uranium is also not renewable because it depletes itself after so much time. Uranium being nuclear fission. Conservation of energy says that energy cannot be created or destroyed, can only be changed from one form to another. You've heard this I don't know how many times in how many different classes, mainly in physics classes, but also probably in some of your chemistry classes. Energy conversion, we want to typically know the energy efficiency when we do a conversion. Entropy is the amount of disorder or what you lose. So when we look at efficiency, we do our power out over our power in, multiply it times 100, and that's in a percentage. This slide shows a variety of energy conversions from fossil fuels, solar cells, looking at a car most specifically. So if we look at this, if I use fossil fuels, I have chemical, changing to heat when it burns in the engine, changing to mechanical, which is what spins the wheels, or spins different parts inside of the engine, which creates electrical to run all the components inside of your car. Solar cells convert it straight from sunlight to electrical. Wind turbines, kinetic, the turbine spinning. which is mechanical, and to electrical. You can see all the different ones. If we're looking at a vehicle and we have it go from chemical conversion, do we want it to go to mechanical or heat? You want it to do mechanical. Mechanical is what gives you movement, and momentum. Heat is typically not good for most cars. Current energy concerns. If you look at this slide, and this slide is a few years old, you look at energy consumption by source. Using a lot of these non-renewable energies, you get pollution, depletion, cost. They're not renewable, so they're not always easy to get. It's all about supply and demand. Typical economics, and asking the question, what roles do engineers have in energy? There are many different types of engineers that deal with just energy and all the different aspects of it. Power is the rate at which work is performed or energy is expanded. We measure power in watts, and 1 watt is equal to 1 joule of work per second. Types of power: we have electrical, mechanical, and fluid power. Electrical, that's kind of a give me. Mechanical power, linear, which is linear or rotary, so car moving or a turbine spinning. Fluid power, hydraulic and gases are the easiest two to know, which are used in many different devices and many different types of machines. Example of power: the student lifted the 50-pound ball 4 feet in a total of 5 seconds. We want to know how many watts of power are used to lift the ball. First of all, we already found the work. We did it earlier in the first example. So I take my work, I put it over how many seconds, I divide it out. Joules per second, say watt. So it's 54.3 watts of power. Very short and quick introduction to work, energy, and power. Once you get in and start actually practicing some of the problems, they tend to make a little more sense and are a lot easier to do.